Good morning, everyone. It's 11 o'clock, so let's get started. This is indeed our very last topic I'll cover for you guys this term. And like I said, it was supposed to be a pizza party. Did anyone bring pizza? Yeah, due to privacy concern, the college wouldn't give me all your addresses, so I couldn't get pizza delivered to you. So sorry about that. In any case, hopefully this will still be worth your while. The concepts in AC circuit analysis. There we go. So a little justification why this particular topic is important and why we do it now, right here. First off, AC circuit analysis really make use of the resistor, the capacitor, and the inductor. So now we are in good position to actually cover all those topics because we've met all these different circuit components, albeit in DC up to this point, maybe with like a switch flipping on and off, but we're going to treat it in AC. So AC stands for, of course, alternating current, which in the simplest form is some kind of sinusoidal. Most people think of it as a voltage source. So, and of course, the voltage through a resistor. We'll go through that. Will give you a current that's also alternating. Where you find this to be used, electrical power is usually generated and delivered using AC because we've talked about how the generator usually works with things rotating in a circle, giving that sinusoidal thing. And then we need the continuously changing voltage and current in order to make use of the transformer to step up the voltage for transmission with lower losses and then step down for more safety in the homes. So that's why electrical power that we use is in AC. So it's good to know how to deal with that. And then through this mathematical thing called a Fourier transform, I'm not sure if you've covered that yet, but it's a theorem basically that says any funky, that's not the function. Any funky function, maybe it looks like, let's draw some actual functions. Any functions of all kinds of forms, that might be some kind of weird sound signal, sound wave or something. You can break that down into a bunch of sums of sinusoidal of different frequencies. If you haven't covered it, don't worry about it. But the upshot of that is that through superposition, because most circuit components, right, has the property of superposition, they're all linear components, you can analyze each frequency independently and see how the circuit affects each frequencies. So this is useful in dealing with, say, signals from sensors. So you can therefore build circuit that does certain kinds of filtering or amplifying particular frequency versus others. So any second year or beyond course on signals and system will be very much involved in this, what we covered today, laying down that groundwork. So, but we're not going to get into super in depth today. This is just a very basic introduction just to get you used to what we have to do in AC. And the terms that we're going to hit today are as such. If you take away these 5 terms today, that should be sufficient to lead you into the first lecture of whatever course you'll go into that covers more of this stuff, right? We got to talk about resistance, but then there's something like resistance called reactance, and then there's this thing called impedance. And then there's this RMS, which stands for roots mean square, and then PP for peak to peak. We'll see all that as we go through the lecture. Okay, so we talked about how in AC, alternating current can be described by a voltage that has a sinusoidal property, right? This V1 is a function of time, right? And so if you graph V1 over time as a sine function, you're going to get it going up and down like that, right? and then it goes on forever technically. So this V naught here, that's the amplitude, right? Calling your sine, so that's V0 and that's minus V0, right? Up and down. And then this here is your, technically your angular frequency. Remembering that it relates to the period, be 2 pi over omega. Right, that's the period. We want to talk about actual frequency. That's 1 over the period. That's going to be omega over 2 pi. And it goes on up and down forever, right? So how does that work if we connect that into a circuit? Symbolically, we represent an AC source, right? This is a battery, right? That's a battery, which is a DC voltage source. And so as an AC voltage source, we put a circle and then we draw this little sine wave in there, and that's an AC voltage source, schematically. So now that we have this source that provides voltage that goes up and down, bigger and smaller over time, what happens we connect in the circuit? Well, the very basic circuit, the most basic circuit we can connect it to, is just simply through a resistor. So resistors in AC. So in this case, it's as simple as something like that. There's your V, there's your R. And anytime you're a resistor, you know that your V is equal to IR. So your current is equal to V over R. So if we plot, say, let's use some color coding here. So V1 is a sine function like that. And then if we plot the current on the same plot, right, that's equal to VO sine, where VO is a constant, then we can kind of make this lump in front into some current amplitude, also multiplied by sine omega t. Same frequency. So it might look something like that. Right? They are completely in phase with each other because a resistor is just simply dividing by the resistant, which is just a simple number. So this is still where your current amplitude is equal to the voltage amplitude divided by your resistance. Just like simple Ohm's law. Understandably easy, right? Simple circuit, simple analysis. Everything matches, everything's great. What is next thing to consider in terms of a circuit is the power that gets used. So power is equal to I times V, which in this case will give you VO sine omega t times VO over R sine omega t. So then the power still has this very similar form to when we had in direct current, right? Power is equal to V squared over R, but it's got tacked onto it this sine square omega t. So how do you plot sine square omega t? Well, it kind of goes up and down, right? And then it becomes negative, but they're both negative. So this is still positive, right? You're still using up power. Boop. Like that. With twice the frequency, because if you know your double angle identity really well, you know that sine square just looks kind of like sine of 2 theta. So that's the power. Which leads us into this idea of the average power, because as you see, the power that is consumed by your resistance, which you can picture like a light bulb, right? And if you have an AC light bulb, it kind of actually flickers, in this case, in North America, 60 times a second. It goes brighter and it goes bright up here, then dark, then bright, then dark, then bright, then dark. It just goes really fast. This is a simple incandescent light bulb, of course, with a LED light bulb. There's other electronics in there that makes things a little bit different. And anyway, details. But the power that gets used goes up and down as the voltage and current both go up and down. So this here is your power amplitude, right? Sort of, kind of. It's like an amplitude, but it's a sine square thing. But usually we're more interested in, we don't really care about how it flickers up and down so much. We just care about, on average, over time, how much power that device uses. So that's what brings us to the idea of average power and root mean square. So we already talked about this is going to be, you can say that sine square omega t, and then you end up with a thing like this. If this is your, if that is that, what is your average power? Well, the nice thing about sine square is that it's just a shifted up sinusoidal. So if you cut it right in half, this chunk completely is equal to that chunk. So you can fill it in like that. So you know that the average power over time is just half of the overall height. So the P average here is equal to that divided by 2. But then, to always have to remember to divide by 2, it's kind of annoying. So we do some other funky trick. We do that, and then we do, because R is not going to change, right? R works the same in DC and AC, so we're not going to mess with that. But if we, instead of quoting the voltage amplitude, we move it within the square and make this square root of 2, right? Because square root of 2 square is just 2. If we quote that voltage instead, then we can work with the average power pretty easily. And in fact, we do that. We call that, this term in here, we take the amplitude and divide by root 2, and we call that the root mean square voltage, or RMS. For most intents and purposes, the function of the root mean square is to help us and facilitate us to talk about the average power without being too clunky about it. There's nothing else that's specific about dividing by root 2, but the dividing by root 2 comes up from the consideration of considering average power. So, a little definition here. So V RMS is equal to the V amplitude divided by root 2. And if that is the case, then we can say that the average power is equal to VRMS square over R. Or you can do a very similar thing, right? And talk about, instead of V square over R, you can also do I square RMS times R, or you can split it between, you can split the root 2's between the current and the voltage, right? In other words, this here is VO over root 2 times IO over root 2 which is VOIO over 2, which is the same total max power divided by 2. So that's what root mean square when terms of AC circuit analysis comes in. And it's pretty flexible in that people often kind of fall into it because we use RMS so much for power. We can easily put in any other context because it's just divided by a constant number. But the original purpose of RMS is to talk about average power. Which, let's see, yeah. So when we talk about RMS, right, I can now say to you that when we talk about our AC power in your homes, does anybody know how much voltage we're talking about? In North America, it's 120 volts at 60 hertz. So then this 120, that's actually quoting the VRMS. That's not the actual amplitude. 220 is in other parts of the world that are a little more sensible to me. Yeah, it's between 110 and 120. So it's like 117, I think it's the official number. So the actual amplitude of the voltage that comes through your wall plug, it's actually, I think it's 117 VAC, right? That's your VRMS. So then your actual amplitude, I'll get this on the calculator. I don't know why I don't have this in my notes. So it's going to be root 2 multiplied by 117 volts, which is 165 volts. So that's the actual amplitude of the thing that comes out of your walls. So the actual function for that would be 165 volts sine, and then because this is hertz, omega is 2 pi f, so that's 120 pi t. So it goes up and down, up and down, up and down. And if this is your V, your period here is 1 over 60 seconds, roughly. Your amplitude here is actually 165 volts. What's often quoted is somewhere around here, this magical divide by root 2. You see, it means nothing in terms of the voltage itself. But when we consider power, we square it, and then we mean it, and then we square root it. Roots mean square. 117 volts is somewhere around there. This is your VRMS, right? So in dealing with AC, it was never wrong to just take the 117 volts and multiply by whatever current, which is also measured in RMS, to get the power. But if you dig into the details a little bit more, the amplitude, it's a little different from the RMS value. And then sometimes, instead of quoting these two numbers, confusingly, we quote another number, which goes from peak to peak. Which is quoted VPP. From one, technically it's peak to valley, I guess, which is going to be twice the amplitude, which will be, I guess, 330 volts. So that's kind of the nomenclature you gotta get used to between amplitude, RMS, and peak to peak. Okay, next, what if we bring in a capacitor? Well, our loop rule still applies, and our junction rule still applies. We know that for a capacitor, let's get something with a little higher contrast here. For a capacitor, it's equal to Q over C, where Q is equal to the integral of the current. Right, in a simple circuit like that, that's all there is. So we know that your input power, it's equal to whatever gets eaten up in your capacitor, or whatever its capacitor is being against, I suppose. So that's Q over C, that's equal to the integral of di dt, right? So if we derive both sides with respect to time, to solve for I, essentially, there we go, dt is equal to I over C. And so I, the current, if we're solving for current, given the voltage, it's equal to C times d dt, and our function for V1 is V0 sine omega t. Sine becomes a cosine, right? Cosine. But don't forget, chain rule, you gotta multiply an omega in front. And so what you end up with, given your voltage, voltage is a sine function like that, with the peak, say, here at pi over 2, your current is a cosine function, positive cosine function, so it does this. Ooh. Oh, let's not put it at the same height. Ooh. 0. Trying to match this up here. Yeah, close enough. There we go. With the peak over here at 0. So that's your I. So it gets so to remember these two relationships, we come up with this mnemonic. You see that the current peak is a little bit in front of the voltage peak with a phase difference of pi over 2. Right. It's also, a phase lag. It's 3 pi over 2 slower, but we talk about the smaller one because it's closer. So it's pi over 2 in front, so you can think of that the current is in front of the voltage. But instead of using voltage, because V is hard to remember, we think of it as EMF. And then for a capacitor, the current is in front of the voltage, or EMF. So you can remember the word ice to remember that, a capacitor, the current, what we call leads the voltage. Ice. So that's the qualitative part of it. To make it quantitative, the thing we want to kind of do is we want to cast this thing to look something like what we had in the resistor. Because in the end, yes, you still get a sinusoidal function of a certain frequency, yeah? But we don't have sine anymore, we have cosine, so we have to do something else there. But the term in front, right, this still gives us the current amplitude, right? Recall in the resistor case, the current amplitude is simply the voltage amplitude divided by some resistance. So if we can we cast it in that form? Yeah, of course we can. We just say that the current amplitude is equal to your voltage amplitude divided by, because it's the reciprocal, something like that. So to find the size of the current resulting, you just divide by this funky term here. So let's name this something. It's sort of like resistance, right? But now there's a derivative involved, so the sine has become a cosine. So we can't call it resistance. Let's call it something like resistance. We call it reactance. And we use a symbol X. So that's where reactance comes in. It's when you have a component that changes the AC from a sine to a cosine. But if we're still interested in just how the amplitude gets affected, we can do that using this reactance number. Very similar to how we would use the resistance number. Let's reason out what the heck is going on a little bit qualitatively. This dependence, xc is equal to 1 over c omega, tells us that if we have a bigger capacitance, we would end up having like a bigger quote-unquote resistance, and therefore the current would go down. Does that make sense? Well, let me say the other part first. If the omega goes up, your xc goes down, because, back up. V is equal to I times xc. Yes, because I is equal to V over xc. Yes, so that's still true when you're my bad. That's why it didn't make any sense. Here we go. So when either of these numbers goes up, the reactance goes down. So you can think of it for the same current, the output voltage goes down. Which makes sense because a capacitor, their job is to resist change in V, right? We talked about how a capacitor resists changes in the voltage by maintaining a certain amount of charge, right? This charge here stops us from readily just putting the voltage in any value. It resists dV dt. So the bigger the capacitor, the harder it is for the voltage to wiggle up and down. But also, the faster you want to wiggle the voltage up and down, the less effect you're going to get because you're changing it faster as well. So that's kind of one way to think about how the reactance of the capacitor has this particular form. But that's just something you can kind of memorize and build and work with. The qualitative takeaway is that this reactance depends on the frequency. Now, this frequency is not the frequency of the capacitor, it's the frequency of the source. So depending on the frequency of the source, the circuit behaves differently. which is something we haven't seen in DC, of course. There's no frequency in DC. So that's an important point to make there. Let's do a similar thing for the inductor, and then we'll put it all together, and maybe you can see how it all kind of works out. So for an inductor, we can just simply put, in an ideal case, an inductor just like that. And in an inductor, the V of the inductor is minus L di dt, right? That's the governing equation for the inductor. And so the voltage, whatever voltage is applied here, gets eaten up by the voltage of the inductor. So that's why V1 is equal to negative VL. So that's positive L di dt. They of course share the same current, which I guess I didn't make that point earlier, but it should be obvious. So then we know that the V drop is equal to L di dt. So if we want to solve for I again, we would integrate with respect to time on both sides. Actually, we'll swap the L over reverse. So V over L, and then we integrate to get simply I, which means that we would integrate VO L sine omega t dt. And so my current over time as a function will have this constant. Sine becomes negative cosine. And again, chain rule, we put an omega in front. Oh wait, no. Chain rule, integrating, we put an omega underneath. So again, we're going to have a V that is of a sine function. And I that now has a negative cosine, so it starts out here, goes to 0 here, and gets the peak over here. Again of the same frequency, but it's got a cosine, and that you can see that the peak of the current now is a little bit in front of the peak of the voltage. So qualitatively, we can say that the I, again, we'll use the EMF for a inductor. So we can use the mnemonic like that. The voltage, wait a minute. Yeah, the voltage comes earlier than the current. That's right. The voltage leads the current for an inductor, and we use the word Eli. So to put both of those funky mnemonic, I know it's a little silly. Oh, the integration constant, we know it's 0. Because at time equals 0, you need to get there's initial condition you can solve for, but if we assume that the initial voltage across the inductor is 0, then everything kind of works out. So if we put both of these together, we can use the mnemonic Eli, the Iceman, to remember which voltage goes in front of the other for the two very similar components of the inductor and capacitor. So again, we end up with a cosine function. So we can again define this thing called the reactance, right? And the reactance is whatever that's got caught underneath here, except we have to include this negative sign. So the reactance for the inductor is negative L omega. Very similar to the capacitor case. Rationale you can think of, if either of these goes up, remember the job of the inductor, or one of the behavior of the inductor, it resists change in current instead of change in voltage. So if you were to increase either of those things, you would increase the reactance and therefore reduces the resulting current. I might have said something wrong for the capacitor case, but I guess you can reason it out for yourself. The main thing is these are the expression we end up with. The bigger the frequency, the bigger the reactance is for the inductor, and therefore the resulting current will be smaller. For the capacitor, the bigger the frequency, the smaller the reactance, so the resulting current will be bigger. Or flip it around and think of the resulting voltage will be smaller. Sorry for the confusion. But the negative here is important. We'll see how that comes into play when we combine these things together. So when you combine these things together, depending on the circuit, how it's all connected, whether they're parallel and series, you can do all kinds of things, but we're not going to get into all that detail. We're just going to stick with this one very simple case of a series LRC circuit. There is a AC source with a inductor, a resistor, and capacitor all in series. So how the heck do we start looking at this thing? Well, anytime we look at, even the most complicated circuit, you can always fall back on your Kirchhoff's rules. What that tells us is that because there's no other branches and junction, you know that every single component has the same current. That you know is true. Whatever derivative or integral, if you solve for the current, you get the same thing. You also know that you have the loop rule. Technically, these are all magnitude because they're all against the voltage source. So whatever voltage the voltage source is applying, by the time you go through all the different components and get back to the source, you should have 0 voltage. So whatever you're supplying gets used up in all of those. So then that's going to let us write, that's my input, it's equal to I, in all cases this I is a function of time which we'll have to solve for, but it's I times R for the resistor plus I times XL plus I times XC. Oh, actually, I'm going to not do that and write something a little more intelligent. So you have the I times R sine theta, or sine omega t, because this is resistant, not reactance, plus IXL, but then because it's a reactance, we're going to use cosine, and similarly for the capacitor. So if we want to solve for the current of a certain size, we would have to add up a bunch of sines and cosines. And then we take this whole big long thing and divide. So anytime with AC circuit analysis with multiple components, you're going to have to add up a bunch of sines and cosines. And unless you're really, really, really good at trig identities, this can get a little tedious. So we come up with a new representation and tool to help us do this a little quicker and faster. And that tool is called phasors. It actually stands for phase vector, and you see why it's called that as I explain it. But the imagining here is that we can represent a sine function or any sinusoidal function as like a vector that goes around in a circle, like sort of like that, given a certain frequency. And this tool that we're coming up with, phasor, is really useful for adding up waves of the same frequency. We assume that everything has the same omega, which is the case of all the things we're trying to add. So the representation is, we represent the sine function as this vector that's spinning in space. Well, how the hell does that make any sense? Well, if you picture it as, if we do the projection, if we plot, say, the y value over time, as it spins, it's going to go up and down like that, which gives you the sine function. So this is the y projection of this spinning representation. Yeah, the thing with phasor diagram is without the animation, people often get lost to why we draw these arrows the way they are. But you're always picturing that these things are always spinning around at a particular frequency. But we're drawing it on a static 2D paper at a particular time. So then, if you just do all your math, like vectors, and then you look at the y projection, it will end up effectively doing what you want to do. Right? Similarly, we can represent another vector with a slight phase shift by drawing that vector at a different angle. So if we were to do the y projection over time, you're not going to start at 0 now because the y projection is up here at time equals 0. And then as this move around, you're going to scribe out your sine function, but with a phase shift. And of course, if you have a cosine function, right, that's basically the sine shifted by pi over 2, sorry. Yeah. So you can represent it as an arrow like that. That's a cosine function. And if you were to sum these two different things up, so again, same frequency, but they with different initial phase and different amplitude, you can imagine that both of these vectors are spinning around at the same frequency, so they do that. And then we can look at the overall sum of the vectors. And if you look at the y projection of that sum vector, it will give you the sum of those two sinusoidal. So we've basically broken down or twisted around the summing of two different sinusoidal with different amplitude and different phase constant, which with trig identity would be like a nightmare to do, into what we very well know of a vector addition procedure, which you probably know very, very well by now, right? You always break it down along the x and the y. So then you know that the AF in the x is equal to, in this case, A1 plus A2 cosine delta phi, right? And then AFY is equal to 0 plus A2 sine delta phi. Notice omega t doesn't come into play here, right? Because the whole thing spins and we don't care about, we're just taking a picture of it at one particular time. Right? Then once you have the two components, which is your AFX and your AFY, then you can individually figure out the actual AF magnitude, which is the square root of AFX plus AFY. And then, and then the actual angle, alpha, I guess you can make it a plus. The actual angle, alpha, would be the arc tangent of AFY divided by AFX. So that's the whole idea of phasors. When you probably get to the actual course that you'll do next, they might introduce this as some kind of summing complex exponential with something of the form of e to the I theta, and we can use complex number to do the math even easier. But the basic idea of the phasor is to represent sine functions as these arrows that spins around on this plane, and we're looking at the y projection of such plane. So let's get back to this lovely thing here. What we have was we had VO sine omega t, which is still there, and then you have IR sine omega t plus IXC cosine omega t plus IXL cosine omega t, like that. If we were to, then we can actually make this into that sum of XC omega t plus XL cosine omega t, right? This whole thing acts kind of like, oh, thanks, jeez, yeah, of course it should. Thanks, Lionel. Still following us here, that's great. This whole thing here you can think of as like the total, something like a resistance. And I'll just even dump the word here. We'll talk about that exactly what it means in a second. But you can think of that as a total impedance almost. We call it impedance. It's kind of like a resistance, right? It's another thing that's like a resistance. But if we do the phasor diagram for that sum, what you see is that you have R, that's a sine function. You have XC, that's a cosine function, positive. And you have, I can write that in. You have XL, which gives you a negative cosine function because XL is negative. So sometimes we just get lazy and say this is like that, and we use the negative of such things. So if we're to sum these things up, we would move head to tail, head to tail, head to tail, right? So we'll do that, and then we'll do that. Maybe it's a little longer, I don't know. And then that's the overall sum. And I'll name this Z for reasons. For convention, I guess. So this Z here plays like the total impedance or the total resistance of the overall circuit, giving you what the current is supposed to be doing. So you can represent the final current function as something like that, where alpha, I guess in this case would be negative alpha, would be a negative number in that case. And so we can still represent the magnitude of the Z. We take the voltage divided by that, get us the magnitude of the current, and then the current will have a certain phase shift based on wherever this Z ends up. So looking at that diagram, you can say that the magnitude of Z is equal to square and R square. And then alpha would be 10 minus 1 R. So based on your capacitance, your inductance, and your resistance, you can work out what the final overall currents will be, which was the meaning of solving the circuit. Now this alpha here this is the angle voltage of the voltage source, the angle offset from the voltage source. So we're defining using the voltage to be kind of the metronome of the whole circuit, and then we're basing our currents off of that. Oh my, I'm so out of practice. I actually made a grave error here. Let's fix that. Let's fix everything. Let's use purple to fix everything. So I swap up these two just because I haven't done it for a long time. I'm so sorry. Because the current, because Eli, right? Oh wait, no, I was right. My notes are wrong. Okay, everything's good. Forget what I said. Everything's so good. We're good. We're cool. We're cool. Oh, I know what my problem is. For mathematical details, that is a little bit beyond this course. Hopefully, I got the idea across. If you want a full explanation why this is, you can talk to me on your own time. I'm sorry, but these two things are supposed to be swapped around. So L is supposed to be the positive one, and C is supposed to be negative one. to represent that we expect a positive alpha, right, which is a shift in that direction for the current if we're using capacitor. So that's why the capacitor, okay. Ugh. So for a capacitor, we remember Iceman, so then alpha would be positive, right? Because a positive phase shift means shifting that way. So that's why some people use minus alpha to make things all work out. Okay, I know that was very messy. So let's do an example and we'll leave it at that. So again, we're going to use our AC source. That's typical of our home, right? That's 120 RMS, 120 V RMS. This is your 60 Hertz. If we supply it and plug it into this inductor, this resistor, this capacitor. Based on the form, we got that. XL is equal to 1. The size of XL, which we often quote as positive anyways, would be 120 pi times 100 millihenry. So if you, this is per radians per second, it actually gives you the units in ohms actually. 7699 ohms. One over omega c, 1 over 120 seconds times 30 microfarads, 88.419 ohms. And then your resistance is just 20 ohms. Your Z, which is your overall impedance, which is basically your resistance plus your reactance combined. But we can't just simply add them because one works with sine functions, one works with cosine functions. So we kind of have to add them like Pythagoras. So we have the R square plus, as I was saying before, we're going to do XL minus XC square. So that's 20 ohms all square plus that all square. Oh. Ah, jeez. Messy note. 37.6. Losing you guys here. Okay. And that number ended up being 54.52 ohms. So we know that the current amplitude is equal to your voltage amplitude divided by the size of your impedance, right? That's just the magnitude of the final vector. And we will get some negative angle. You can also use radians. Actually, you should use radians because we're going to be putting that into our sine and cosine function. So I'm putting it all together. We will see that. Oh, I know what happened. Okay. I went and changed all my notes this morning, and then I'm confusing myself as a result of that change. So if this is the starting value, you're going to have the current having the same omega, but I put minus here. That's what made everything all make sense now. Because we think of alpha to be a positive alpha would give us a shift to the right, which is VO over Z sine 120 pi t minus alpha. So then we work that out to be 3.03 amps sine same omega t minus, which gives us a plus 1.20 radians. And it makes sense because our impedance of the capacitor is bigger than the impedance of the inductor, so we expect the capacitance behavior to dominate, so current comes earlier than V, right? ICE. That's why we expect a phase shift that is positive. Shift to the left. So given this V, you will get this I. One more concept I'd like to cover before the final wrap up, running a little long here, sorry, is the idea of resonance. If you look at the form of our overall impedance, right? Z would be the smallest, and therefore I would be the biggest when XL minus XC is equal to 0, right? Because you're just summing squares. The only way to get the smallest number is if one of the things inside the square is 0. R is not going to change no matter what. Which tells us that omega L minus 1 over omega C is equal to 0. So therefore, if we solve for omega, we get that. So for a particular we have the maximum current response for this particular frequency, right? The resistance is not going to change no matter what frequency you put in, but the reactance of the inductor and the capacitor changes. And so, in particular, this one very special frequency gives us the biggest possible response. And hopefully that looks familiar, because that is exactly the resonance frequency for a simple LC oscillator. Hopefully to no surprise. And at that frequency, you can get the biggest possible current, and also your phase shift will be 0. Right? Because 10 minus 1 of 0 over R would give you 0. So that's at resonance. So thanks for sticking with us. Quick final wrap up. If you don't get all the math today, that's perfectly fine. When you get to the next course they'll teach you phasers all over again, and they'll teach you how to do phasers with complex exponentials, so you can deal with the cases of not just this simple series circuit, but with things in parallel, with combination of parallels and series. But if you take these 5 words away and know what that mean, that's all I expect you to remember into the next course. Resistance, we already know, right? That's the simple resistant thing. Same as always, right? A resistor has resistance. V equals IR, right? That hasn't changed. This reactant things is somewhat like a resistance, but it includes some kind of power to phase shift. And that's for the capacitor is 1 over omega C. For the inductor is omega L. The impedance is the combination of R and X. Specifically is your Z as a magnitude is equal to R squared plus X squared. And then we also talk about this root mean square thing, RMS, is equal to over root 2, which is related to calculating average power. So hopefully you're not mystified by the RMS notation anymore. And then sometimes some people get a little antsy and they use this peak-to-peak thing, which is basically equal to twice the amplitude. But for signal that are offset, that might be more useful to talk about. So if you just take away those 5 terms, you're well set up for your next course. So that brings us to the end. Thank you for showing up again. Sorry for all the little mumbo jumbo. We only do this once a term, so I'm so sorry. But hopefully some of the points get across. And thank you for a great term. It's been a great pleasure to meet and work with every one of you. Some of you for 2 terms in a row. That's always a little bit special. You might have noticed that I've included a link to a song in the video description. That's something that my wife, who's also a physics teacher, and I kind of dreamt up and gave birth to because we were spending too much time at home. If you had at all enjoyed the silly electromagnetic spectrum song yesterday, you might get a good laugh out of this one. Anyway, I'll just leave it at that. But thanks, and we will. If you have any question, of course, please let me know. I'll stick around for another couple minutes. And you're all very welcome. Best of luck wherever you end up, and see you around. I'll just gotta say it was mostly her idea. She did all the music too. Quite quite amazing in that. And of course, moving into the future, any physics course you take will probably be quite an adventure, and that's partly what drew me into studying physics in the first place. Because every single course you take from now on, moving into modern physics, even statistical mechanics, thermodynamics, they're all mental gymnastic, and they're like these mental adventures you go on, and you come back like see the world a little differently, and that's why physics is amazing. So keep it up, and I'll see you around. Bye bye.